Amide hydrolysis, very like nitrile hydrolysis, subject of my last video, but much more important. Let me tell you why. Remember, all hydrolyses are just addition of water. So if we do a little bit of chemical arithmetic here, and we add water across the CN bond in this secondary amide, remember, secondary amide has one N-alkyl substituent, draw everything in the same orientation, and we've cleaved that bond. It's good to draw in the same orientation because then we don't lose atoms. But now let's tidy up the structure to make the hybridization states more realistic. Here we go. We formed a carboxylic acid and an amine. After that, the rest is history. The amine may deprotonate the carboxylic acid, probably will, and so we'll be left with the carboxylate. Now, what if that amide was part of a chain? Well, if we did amide hydrolysis, we'd cut the chain at that amide bond. If that chain is a peptide, and we could cut selectively at one amide bond, then we cleave the peptide into two smaller ones. And this is why acid-mediated amide hydrolysis is so important to most students studying organic chemistry, because most students taking introductory organic chemistry are life science majors. When we eat, we generate insulin. Insulin is part of the digestive process. When insulin is made in the body, expressed, it actually is made first as a bigger protein. And when you have a bigger protein, to get cleaved to a smaller one, we call that a proprotein. Proinsulin is cleaved into insulin. Here is insulin, and you can see the two cleavage sites there. Very similar, both basic. We don't need fragment C, throw it away. We need fragments A and B, and they get joined together by disulfide bonds, actually, to give us the hormone that we need. For another example, let's look at a day in the life of HIV virus. The virus wakes up, gets out of bed, and like a lot of us in the morning, it feels like, I want to reproduce here. So it goes to find a healthy cell, finds a receptor on that cell where it can get endocytosed. Once it's inside the cell, the virus has a problem because it's an RNA virus. It's a little bit of a special one. It has to generate DNA. So that's reverse transcription. After reverse transcription, the DNA, which encodes for the virus, is inserted into the host DNA. And then the host unknowingly takes over and it replicates everything. It generates big peptides. When the host and the viral DNA are expressed as proteins, then the viral proteins are larger than they need to be. They need to be cut if the virus is to propagate. So the virus uses proteases to do that. Proteases perform amide hydrolysis. If we're a medicinal chemist or if we're in a pharmaceutical company and we're trying to prevent the propagation of HIV virus, we could block the receptor, we could block the reverse transcription, and that's actually how the first drugs for HIV were made. AZT was one of the first. We could block the integration process, and finally, we can block that cleavage with protease inhibitors, compounds that interfere with the amide hydrolysis performed by proteases. Okay, this is all very interesting, but it's well ahead of where we are now. To understand proteases, you need to understand the chemistry of amide hydrolysis. So what's the mechanism? In acid, protonate to activate. Protonation of the most basic site in an amide, which is the oxygen, activates the amide towards nucleophilic attack. Protonation of the oxygen is facilitated by the nitrogen lone pair pushing in and forming a C-N double bond. Push, push. That generates an sp2 hybridized intermediate. A nucleophile now is going to add to the carbon. And in hydrolysis, that nucleophile, of course, is water. Nucleophilic attack of water. What atom is it going to add to? Of course, it's going to add to the carbon. It can't add to nitrogen because there's 4 bonds to nitrogen already. So we push into the carbon and push the electrons onto the nitrogen, neutralizing it. That gives us a tetrahedral intermediate. You can see the fragment of water that we've added. That's great. But we need the nitrogen to leave. How do we arrange that? The way that we arrange that is take a proton off the oxonium ion that we generated and put it on the nitrogen, making it a better leaving group. Otherwise, it would have to leave at NH2 minus. That's bad. And I think the best way to show that proton transfer is via a water molecule. So the electrons can push around from the most basic site, that's where you put your pen, on the nitrogen, push, 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 push to break the bond. So water and ammonia is liberated. And if we keep everything in the same orientation, we get this protonated carboxylic acid. For deprotonation, let me tidy up that diagram of the carboxylic acid. Loss of a proton gives us the carboxylic acid product. And as I say, this is probably ionized in solution. It exists as a carboxylate ammonium salt. I hope that helps you with your studies. Thank you very much for listening. Bye-bye.